So in the last session, we were discussing about hydrodynamics. And we had seen about steady flow or streamline motion. Of an ideal fluid. So the two important equations that we apply to this kind of situation when an ideal fluid is in steady flow are respectively continuity equation and Bernoulli's equation. So if we consider two positions in the tube of flow where the area of cross section is A1 and A2. Okay. The velocity of flow is V1 and V2. Okay. And the pressure of the fluid inside, the absolute pressures are P1 and P2. And also with respect to some standard horizontal reference level, the vertical height of these sections are H1 and H2. Then the equations by which we can connect these 2 points or connect the properties of the flowing fluid at these 2 points are respectively continuity equation or in general, the product of A into V is uniform because the volume flow rate is uniform. And the second is the Bernoulli's equation. Okay, so this is the point till which we had reached in the last lecture. So today we'll look at the applications of this concept in numerical problems. Okay, so let's understand the application. So for example, we have a situation like this. A horizontal pipe whose cross-sectional area is tapering. Okay. So suppose A1 is 20 centimeters square, A2 is 10 centimeters square, V1 is 0.5 meters per second. So first of all, find V2. And the volume flow rate. In cubic centimeters per second. Third, we want to find the pressure difference in pascals. Okay, so this is a direct application of Bernoulli's equation and continuity equation. So the first part, use equation of continuity. And that is equal to only volume flow rate. Okay, so for the second part, use this. For the third part, use Bernoulli's equation. But in this, use the fact that H1 is equal to H2 because it's a horizontal pipe. Okay. So just use this to find the numerical values and send me the answers. Okay. Then we'll discuss the next question. Okay, so Aruja, Rahil, Varun Yadav and Varun Kumar, all of you have sent me these answers. Krupa. So let's discuss. Excuse me. So first part, for example, from A1 V1 equal to A2 V2, we can see that V2 will become twice of V1. So it will become 1 meter per second. Okay. And from this, we can see that volume flow rate become product of area into velocity. So this we can write as 20 centimeters square into 0.5 meters per second or 50 centimeters per second. So that is 10 raised by 3 cc per second. Okay. Or it is, in fact, you can also see that it is 1 liter per second. Okay. Now from this we can see that P1 minus P2, this pressure difference, is equal to half rho V2 square minus V1 square, because H1 is equal to H2. Okay, so this will give us the pressure difference in pascals. Okay, so hope the application is clear to all of you. Yes, 375 pascals or 3.75 into 10 raised by 2. Okay, so next we will see the application of Bernoulli's equation in a particular apparatus or device called the Venturi meter, which basically works on this kind of principle. So this is an apparatus So suppose we have a horizontal pipeline through which fluid is in steady flow continuously. And we want an apparatus which will give us the value of volume flow rate in between. So we know, for example, that this area of cross section is some A. So what we do is in between somewhere we insert this kind of device, which consists of this thing that the pipe is tapered, okay, and also where it is tapered and where it's at its normal area of cross section at these two positions, there are two vertical capillaries which are built into the device. Like two narrow vertical tubes. Okay. Narrow tubes, as you know, are called capillaries. So we have an ideal flow, which is in ideal fluid, which is in steady flow like this. So what happens is that the fact that the cross section here is lesser, let's assume the cross section is some E2 here. So the velocity of flow becomes more. Okay. Whereas in comparison, the cross section here is A1, the velocity of flow is V1. So A2 is, let's say, A1 divided by N, where N is a factor greater than 1. Okay. So that creates a pressure difference, because of which the level of liquid in the capillaries is going to be different. And we can measure this level difference externally. So this is H, this level difference. So the pressure of the liquid at this point is P1. The pressure of the liquid at this point is P2. So you can see that P1 minus P2 is going to be rho G H. Okay. This is from hydrostatics of the vertical column. Okay. Then by Bernoulli's equation, or before that by continuity equation, with this relation. Okay. And finally, we'll now apply Bernoulli's equation. So we have P1 plus half rho V1 square is equal to P2 plus half rho V2 square, because we are in a horizontal pipe. So H1 is equal to H2 at the 2 points that we are considering. Okay. H1 and H2 don't have to do with the vertical column of liquid above. They have to do with the position of the point 1 and 2 vertically with respect to a horizontal plane. So that is H1 is equal to H2 because it's a horizontal pipe after all. Okay. So now from equation 3, we can see that P1 minus P2 is equal to half rho V2 square minus V1 square. Okay. Now substitute from equation 1 this pressure difference. Okay. And here substitute from 2 from continuity equation. So we get rho GH is equal to half rho V1 square into N square minus 1. So we get the velocity of flow at this point is square root of 2GH upon N square minus 1. So the volume flow rate okay, so this becomes the formula. Okay. So obviously N is a known quantity here, because we can measure the cross sections at the two positions A1 and A2. So the ratio N is known, and H is a measured quantity. So from that we can measure the volume flow rate. Okay. So capital A and N, they are known quantities. H is measured. From that we can find volume rate. Okay. So this is a standard apparatus used in fluid mechanics. Just make a note of this quickly. We'll discuss the next thing after this. Okay, so this is the standard formula for velocity of, for venturimeter and measurement of volume rate of flow. Now, next application we will see is the measurement of what is called speed of efflux. Efflux is the opposite of influx. So we have a situation like this, that we have some sort of an open tank. Which has sort of a small opening at the bottom. So this kind of opening is called an orifice. Okay. That is very narrow area of cross section. So it is called an orifice. Okay. We have some kind of fluid. So as you know, water will come out at high velocity from the orifice, and that is called the speed of efflux. So to find out the speed of efflux, what we do is we visualize the streamlines. Like this. And we take one point to be at the surface and the other point to be like this. So when we apply continuity equation, we can see that A1 is the area of the tank. A2 is the area of the orifice. Okay. So A1 is very much larger compared to A2. So V2 is very much larger compared to V1. Now V2 is nothing but the efflux velocity. Okay. And therefore V1 is very small compared to the efflux velocity. So this is our first thing. This is what continuity equation tells us. Now next thing, application of Bernoulli's equation. Okay. So this is the level difference H between these two. So and pressure at the point 1 is equal to pressure at the point 2 because that is atmospheric pressure. Okay. Point 1 is open surface. So obviously the pressure is equal to atmospheric pressure. And point 2 is a point just outside the orifice. Okay. So again, the pressure is equal to atmospheric pressure. That's why this thing. Okay. So P1 plus half rho V1 square plus rho G H1 is equal to P2 plus half rho V2 square plus rho G H2. You can just write it like this first. Okay. Now we substitute all this information here that V2 is speed of efflux and V1 is very small compared to speed of efflux, and H1 minus H2 is equal to H. So from that next step, we will get the value of the efflux velocity. So just note down up to here, we'll discuss the final step, or you can substitute and work it out yourself. Okay. So again, this is a standard formula that you have to memorize that we get from this.
Sir, what is H1 and H2?
H1 and H2 are the heights of the 2 points that we have considered. Na? The one just outside the orifice and just on the surface with respect to some standard horizontal level. So you can take the standard horizontal level as the level of the floor on which the tank is kept. Na? So the important thing is H1 minus H2 is equal to H, the level of water. Is it clear?
Yes, sir, yes.
You know, so we need not substitute individual values of H1 and H2. No? We can just substitute the H1 minus H2. Height difference is H, right?
Yes.
Okay, so on substituting in this, we will get left hand side is approximately half rho efflux velocity square. Okay, because V1 is very small compared to efflux velocity. Okay. because basically from this, what I'm doing is I'm taking so we get an interesting result that the speed of efflux is the same equation that gives us the free fall speed through a height of h. If an object falls freely under gravity through a height of h starting from rest, the speed it will have is the same as the speed of efflux over here. So it's an easy formula to remember on the basis of that. Yes, so this is a standard this is a standard formula that you have to remember. This is equal to P naught, okay? Just to answer your question, Varun, P1 is equal to P2 equal to P naught, na? Because they are both like open points, na? Exposed to atmospheric condition. So it's equal to P naught, okay? Atmospheric pressure. So this is the standard formula that you should remember. Now next we'll see. So this completes the derivations and formulae part of hydrodynamics. Okay. Next we'll see some numerical examples. So for example, we could have something related to the application of concept of speed of efflux. But with a slight variation. One is, of course, you can get direct formula-based questions in which you have to apply the standard formula, like the speed of efflux formula. But you could also get some variation questions like the next one I'm showing here. So in this, what is happening is that the orifice is made somewhere here, let's say like this. Okay. And the level of water is like this. Okay. So if this height of the liquid column is h initially, but this is made at a depth of x, then the liquid that is coming out from here come out horizontally with a speed equal to the efflux speed. But from there, it will not continue horizontally, but rather will be in a projectile motion kind of situation. So if this range that it achieves is r, so we have to find efflux speed as a function of x, then this range r as a function of x, and we have to find the maximum possible range. Okay, this is given that okay. So just try out this question. We will discuss this. Yeah, just try out this question, people, and send me the answers. We'll discuss in a couple of minutes. Varun Kumar, your answer is correct. Maximum range will be 20 meters. Okay. I'm checking all the answers. Yeah, root 2 GX, Varun Yadav, Varun Kumar, both of you got the right answer. So from that, you will get the range as square root of 4x into h minus x. So for x equal to 10 meters, you will get the maximum range, and the value of that maximum range will be 20 meters. Very good, that's correct. So just by applying Bernoulli's equation, you can see here that here we won't take h in the formula of Bernoulli's equation because h is the level of water which is above the orifice. So we should take the value of h that we take in Bernoulli's equation as x over here, between these 2 points. So by applying again that same kind of thing, like you take this as your 0.1 and this as your 0.2. So V1 is very small compared to V2, and V2 is equal to speed of efflux. And this time you take H1 minus H2 as x. You will get that efflux speed is square root of 2gx, or in this case, square root of 20x. Okay, because we are taking g as 10. So once we get that, now from here it is like horizontal projection. Okay, so something is thrown like this from the ground level at a height of y equal to h minus x. Okay, so if it starts from here at t equal to 0, by the time it reaches here, half gt square is equal to y. So the time of flight is equal to square root of 2y by g, or square root of 2 times h minus x by g. So this horizontal range becomes the efflux speed into the time of flight. So as a function of x, the speed of efflux, the range becomes like this. This is as a function of x. Okay. And then from that, the third part, for maximum value of range, okay, put dr by dx equal to 0. Okay, but you can do it also like this, that range is equal to 2 times square root of some function of x, where that function of x is very simple. Okay, so maximum range will be 2 times this. So we need to maximize this function. So for maxima minima, just use that concept that the function is, so derivative of the function is f prime x is equal to 0 for x equal to h by 2 or 10 meters. So this function's maxima is equal to h by 2 into h minus h by 2, h squares by 4. So range is maxima becomes 2 up into square root of this function's maxima. So maximum possible range is equal to h, which is equal to 20 meters. But this range is maximum for x equal to h by 2 or 10 meters. Okay, so when we make the orifice at a depth of 10 meters, which is exactly the midpoint of the vertical height, that is when the range comes out to be maximum. Yeah, so Aruja, I hope you understood why we are not taking h as 20 here now, because we are applying Bernoulli's equation to these 2 points. No? The point just outside the orifice and the point on the surface of the tank. No? So उन दोनों के बीच height difference कितना है? It is only x. So you're comparing this point with this point. So this height difference between these 2 points is x. So h1 minus h2 is x in Bernoulli's equation. That's why this is coming out like this. So hope this point is clear, Aruja. Very good, Siddhi. Your answer is also correct. Okay, people. So this is another example of application. Okay. Now let's move on to another type of question. So the working principle of a syringe, something that will be very standard for you aspiring doctors. So when this piston is pushed with an force F, then liquid comes out from here with a speed V. So we consider this to be more or less horizontal. Now you can consider this to be a point 1 and this to be a point 2. And we can also consider this to be an orifice. Okay. So if this has area A, so A1 is equal to A and A2 is very, very small compared to A1 because we have an orifice at the other end. Okay. So A1 V1 is equal to A2 V2, means that V1 is very small compared to V. So now applying Bernoulli's equation. So this V2 is the V that we are trying to find out. V1 is very small compared to V. P2 is atmospheric pressure, but P1 will be atmospheric pressure plus F by A, because we are applying the force F at the piston of area A. So Okay, people. So hope this application and question is also clear. Varun, we haven't taken kinetic energy as such. What we have done is we have applied Bernoulli's equation. You know, between point 1 and point 2, this Bernoulli's equation, and they are at the same horizontal level. So H term is not there. H1 is equal to H2. Okay, hope you understood. Okay, so hope that point is clear, Varun, that it's not a work energy equation we have written directly. It's Bernoulli's equation. Of course, that is derived from work energy relation, but in fluid mechanics, we use Bernoulli's equation directly along with continuity equation. So this is the result from continuity equation. Okay, but because of this area consideration, this becomes a relation between V1 and V2. V2 is of course the speed V with which the liquid is coming out. Okay. Okay, people. So with that, we complete fluid mechanics. Okay, next chapter we'll be looking at will be properties of matter. So we will be starting with elasticity in the next lecture. I don't think you should have much difficulty with the questions of fluids because it's more or less direct application type of questions. Anyhow, if you have any difficulty with any of the questions, you can always send me. I will send you some hints or couple of equations how to solve. Or if required, we can discuss some of the doubts in the next lecture. We can keep aside some time. But as I said, I don't expect, I think fluid mechanics is very straightforward chapter, formula based, especially at NEET level. Okay. So that's it for today's session, people. Wish you all the best. Thanks for attending. Next time, as I told you, we'll be starting with elasticity, which is the first section of properties of matter. And after elasticity, we'll be doing surface tension and viscosity. So that will complete this entire section of fluid mechanics and properties of matter. So wish you all the best. That's it for today's session, people. Thanks for attending. Yeah, for the assignments, you can do section 1 or assignment 1 from your module, which has the single option MCQs, right? Last time I have resent the module PDF also in case you don't have the hard copy of the module, okay, which is otherwise also available at the centers. Okay.
So,
Yes.
so can we find total pressure by integrating?
Sorry, can we find what?
So total pressure of fluid by integrating height by taking limit 0 to h height.
But pressure for what, beta? मतलब hydrostatic or hydrodynamics?
Hydrostatic.
तो हाइड्रोस्टैटिक में इंटीग्रेट करके ही तो वो फॉर्मूला आया था ना रो जी एच, उसके डेरिवेशन में ही है. So once we have the formula for hydrostatic pressure, why we need to do integration again? You understanding?
Okay.
No, we directly use the pressure gradient formula, no? And from that we get the pressure difference.
Yes.
Delta P by delta Y is rho G, using that.
Okay.
No?